And let's get started with the first talk by Yves Kwan from Princeton. And the topic is a survey of strongly correlated phenomena in supermoiré materials.
All right, yeah, thank you for coming. Let me just cite this. Yeah, so my name is Yves. I'm a theorist at Princeton. And yeah, first I'd like to thank the organizers for inviting me to give a lecture at this nice school. So I was asked to give a lecture on broadly on moiré materials, and I struggled to whether I should give a talk on my own recent work, but I decided to give a talk with a more pedagogical focus. And so this is probably familiar stuff to those of you who are experts in the field, but I hope this talk will appeal to those of you in the audience who maybe have heard a talk or two about moiré, but haven't really worked on it before. So I can't really mention moiré without talking about the material that really started it all, which is a magic angle twisted bilayer graphene. You see my laser, but magic angle twisted bilayer graphene, or TBG, which is sort of, I've schematically showed with this sort of figure here. And let me motivate this talk by posing the following puzzle, right? So, TBG is just two sheets of graphene that are rotated, some twist angle. So let me try this. Much better. But graphene itself is not known to be a strongly correlated material, right? It's just PZ orbitals, right? But yet, when you take two sheets of graphene and you twist them with some false twist angle, you can get a whole bunch of interesting correlated phenomena, as sort of I've tried to indicate with this collage that I've stitched together here. So let me try and explain how this all comes about. So let's see. Oops. Yeah, so this is the outline of my talk. So in the first half, I'm going to consider TBG in particular. And I'm going to try and argue that through some very basic arguments, we can already make a lot of progress in understanding the key points about this material and understand sort of the basics of moiré physics. And then I'll say a little bit about experiments and some of the challenges in dealing with this material theoretically. And depending on how much time I have left, I will talk about cell battery. I'll talk about materials beyond TBG. So, there's an ever-growing catalog of moiré and super moiré materials, and I'll try and say a few things about those. Great. So let me start with a very quick refresher, right, on just monolayer graphene, right? So as you all know, it's this honeycomb of carbon atoms, and there's two sublattices, A and B, and the lattice constant, and let me introduce a sublattice index, sigma. And the lattice constant of graphene is, angstrom scale. And the simplest model consists of nearest neighbor hopping of PZ orbitals with some electron volt scale hopping, T. Here, I've just drawn the Brouillon zone. It's a hexagon. But I've indicated some important high symmetry points, in particular the valleys or the corners, K and K prime. I've also indicated the reciprocal lattice vectors B1 and B2. And on the bottom right, I've just indicated the band structure of this material. And this band structure famously has Dirac points at the corners of the Brouillon zone at K and K prime. So because we'll be interested at low energies, let's zoom in on these Dirac points, which I'll index by a value index tau. And what I can do is I can Taylor expand the block Hamiltonian about each valley, and I'll get the Dirac Hamiltonian, right? So this Dirac Hamiltonian is a 2x2 matrix in sublattice space, and there's a characteristic velocity Vf. And let me point out that these two Dirac points at the two valleys have opposite winding numbers, as indicated by the directions of these red arrows. There's also some important symmetries. So for example, there's C2 and time reversal. And let me point out that C2, so this is the in-plane rotation symmetry. This forbids a sublattice mass, or sigma z, because it violates the C2. So this term would have opened up Dirac points in your band structure. But let's say, just for curiosity, you were to break the C2 symmetry, for example, by aligning with, say, the HBN substrate. So this would impose a sublattice mass, sigma z, and this would gap out the Dirac points, as you can see here. And this would generate a bunch of Berry curvature, and if you study the continuum Dirac theory for one valley, you will know that you will generate a Berry flux of pi and minus pi in the conduction and valence bands. But of course, we have to remember that these valleys are connected in the UV, right? They're really bands, right? So the time reversal symmetry means that the total Chern number of the two bands are both 0. These are topologically trivial bands, right? And this makes sense, right? Because you need to apply a time reversal breaking Haldane mass, like sigma z tau z, in order to create Chern bands. So let's keep this in mind for later. Okay, so with that quick refresher, let's go back to twisted bilayer graphene. And so our goal is to understand, how do we get from this strange, complicated structure to something that apparently, at the magic angle of around 1 degree, hosts some very flat bands, and in the presence of interactions, yields a bunch of interesting correlated phenomena like correlated insulators, superconductivity, time reversal breaking, and the Kornett-Solomos Hall effect, and much, much more. And to do so, I'm going to use a series of very simple back-of-the-envelope arguments, right? And I'm going to try and answer some very fundamental questions about moiré. So first of all, how do we even understand the notion of a moiré periodicity? How do we understand the notion of flat bands, right? And where do we get this idea of a magic angle from? Are these bands even topological? And finally, is this picture of TBG realistic, right? Is that actually what the material looks like? So let's try and address the first problem, moiré periodicity. So I hope you can see from this sort of schematic that there's this emergence of this sort of moiré pattern, this sort of beating pattern. And the period of this pattern is rather large, right? It's much larger than the microscopic lattice scale, which is set by these tiny little hexagons here. And what you're really noticing, or what your eyes are really tracking, is the modulation of the local stacking orientation as you move across the system. So for example, if you're over here, you're in what we call AA stacking, right? We have hexagons on hexagons, right? But as you move across the system, let's say from here to here, you end up in BA stacking, where your honeycombs are shifted, and eventually, if you move far enough, then you move back into AA stacking. So this is sort of how you can see the moiré period, but to understand the moiré periodicity more quantitatively is actually easier to work in momentum space. So what I've done here is I've just taken the graphene Brouillon zone, and I've drawn it for each layer, 1 and 2. And of course, the 2 layers are slightly rotated, right? And I've also drawn the one of the reciprocal lattice vectors for each layer. And these reciprocal lattice vectors are important because they're a dual encoding of the discrete translation invariance. But because of the twist angle, these reciprocal lattice vectors are slightly misaligned, right? And what happens is that actually the difference of these 2 lattice vectors, which is B sub m up there, this is what this moiré reciprocal lattice vector is actually what sets the moiré period, right? So to see this, let me consider, for example, an electron which initially lived on layer 1 with this X momentum, right? Now, it can Bragg scatter through B1 back to the gamma point, right? So let's say it now ends up here, but then we can then choose to tunnel into the other layer, right? It can become a blue electron on layer 2, and then it can Bragg scatter with B2 back to that plus momentum up there on the top right. And basically what we've learned is that, under the dynamics of the moiré pattern, right, this cross and this plus momentum are actually coupled, right? And so this is showing you that momenta that are related by a moiré lattice vector, moiré reciprocal lattice vector are actually equivalent under the moiré pattern, right? Okay, so you can, if you do the geometry, you can show that this new moiré reciprocal lattice vector is basically related to the original lattice vector B, but scaled by a factor theta, where theta is a twist angle. And for the magic angle of 1 degree, this inverse scaling factor 1 over theta is around 60, right? So, because the reciprocal space shrunk, so clearly the real space must expand. And so you've basically gone from a lattice scale of a few angstroms to a moiré period, which is roughly 10 nanometers, right? So basically, a moiré unit cell is now really big, right? It contains basically 60 squared of the original number of unit cells, and so one moiré unit cell can contain thousands of carbon atoms in it. If you also do the analysis carefully, you can now construct the new Brougham zone, or what we call the moiré Brougham zone, or MBZ. It's just given by this tiny little gray hexagon over here. I've drawn it for valley K, but of course there's also another one for valley K prime. And the reason that I can draw two separate mini Brougham zones is because they're so far apart in momentum space that, to a good approximation, I can treat valley as a conserved quantum number. So that's why I can draw a separate moiré Brougham zone. And so I've just zoomed in into the moiré Brougham zone. And I can again label the high symmetry points. Now they have a subscript M for moiré. And clearly the moiré bands will have to fold and fit within this new moiré Brougham zone. Of course, I shouldn't forget that we have still a spin and valley degeneracy, so there's really a four-fold flavor degeneracy. And in the moiré community, we often define a very important number called the filling factor, mu. This is a dimensionless number which basically measures the number of electrons per moiré unit cell. And this is measured with respect to neutrality, so mu equals to 0 corresponds to charge neutrality. Good, okay, so I've told you about how we can understand the moiré periodicity. So how do we then understand the notion of flat bands and a magic angle? So clearly the moiré band structure has to descend in some way from the Dirac points of graphene, right? So let's consider a one-dimensional momentum cut, this green line, which cuts through the Dirac points. And let me first consider the limit where the layers are decoupled, where they don't talk to each other. In this case, I can draw the energy spectrum as a function of momentum along this cut. It's just the Dirac points of the two layers, right? And these Dirac points will clearly intersect, right, as you can see here and here. And the energy of this intersection is basically set by the slope of this line, which is the Fermi velocity, and the spacing between these Dirac momenta, which is set by the twist angle. And if you plug in the numbers for the magic angle of 1 degree, you find that this energy is around 100 millielectron volts. Now, let's slowly turn on this interlayer hybridization, right? Let's allow the electrons to tunnel between the layers. This is how the layers know that they're in a moiré material. And what will happen is that you'll get avoided crossings whenever these bands cross. And basically, this band crossing will be pushed up and down, and you'll form moiré bands, which are given by these sort of gray bands up here and down here. Now, you can estimate this splitting, right? This is T perp value. And you can estimate it by just looking at untwisted bilayer graphene. And you find that this value, this interlayer hopping, is around 100 MeV. So basically what happens is that at the magic angle, there's this magical coincidence of energy scales where these bands get significantly flattened and form these really flat bands whose bandwidth can be as small as a few millielectron volts. And at the same time, these bands seem to be separated from these remote dispersive bands by a rather large energy scale. Okay, and just to be clear, we have to remember that we actually have 8 bands because we have the 2 Dirac, and we also have a factor of 2 from spin and 2 from valley. But to really call bands flat, we have to compare them. We have to compare the bandwidth to an interaction energy scale, right? And so the interaction energy scale, can be estimated by considering the Coulomb energy between two electrons at a distance of 1 moiré length, right? And if you plug in the numbers, you get an energy scale of around 20 millielectron volts, right? So this motivates the notion of a magic angle regime where the bands are significantly flatter than the interaction energy scale and are separated by rather large remote band gaps to the remote bands. And the idea is that all the interesting correlated action is happening within these narrow bands. Okay, so I hope that motivates why we can get flat bands and only within some magic angle range. Now let's ask whether these bands are topological in some way. So let's go back to our narrow bands. And we have to now remember that, okay, we have C2 symmetry still. Yes? So I guess you're referring to the chiral limit where the bands really become exactly flat. I don't think there's a simple symmetry argument there. It is quite a cool result, but I don't think there's a simple way to motivate it. So let's go back to this picture. We still have C2 symmetry, so the Dirac points are still there. But we have to remember that these Dirac points actually descended from the same valley in graphene, right? So actually their winding numbers are the same. So this time, if you apply a sublattice mass, sigma z, you get the Dirac points, but if you repeat the same exercises before, you find that you now generate Chern bands. Of course, we have to remember that we have time reversal symmetry, so what really happens is that the opposite valley has the opposite Chern numbers. Right? But these are really genuine Chern bands, and the moiré is important in basically like caging the Dirac points in the moiré-Brouillon zone and locking in the Berry curvature. So what you find is that you now have these valley Chern bands. And from this perspective, it's now maybe easy to motivate why you may get interaction-induced Chern insulators, right? So let's say we're at some fixed filling, like nukes to 3, right? So at nukes to 3, you have to fill 7 of these 8 central bands. And if you have strong interactions, then you may want to reduce the exchange energy by polarizing, by inducing spin or valley ferromagnetism. So this is what I've done here. You can see that I've filled, obviously, the remote bands, but I've also filled 7 central bands, but I've left 1 band, which is K and spin down, empty. And this is now a Chern insulator, right, because there's a net Chern number. And this is sort of one way to motivate experiments, transport experiments, which indeed measured a quantized anomalous Hall resistance at this filling nukes to 3. Right, so I've just pulled up the abstract of that paper here from Andrea Young's group. And indeed, you can see the ingredients, right? So, you need alignment of the hexagonal boron nitride to TBG. You have intrinsic strong interactions, which lead to spin and valley polarization, and hence a Chern insulator. Okay, great. So now we've sort of understood that, okay, there is at least a latent topology in these bands. Let me finally address the final question, whether this picture of TBG is realistic. I mean, I made this in Microsoft Paint, so I just twisted 2 lattices. So the point is that this is a rigidly twisted bilayer, right? But I told you that a moiré unit cell had thousands of atoms in it, right? It's a complicated beast, right? So who knows what happens in the meanwhile? Like maybe these atoms migrate, they relax, right? All sorts of things could happen, and it's not clear that this is still a good caricature of the actual material. So one way to test this, whether it's a good caricature, is to just first assume a rigidly twisted bilayer, and then compute quantitatively the band structure, and then see what happens. Does it agree with experiments? So let's do that. And I'm going to appeal to the so-called Fitzgerald-McDonald model, or BM model. This is a rather popular way of generating the single particle band structure in moiré materials. It was pioneered by these guys in 2011. I think that's an Amber Alert. And basically, it's a rather simple model. Remember that we have effective valley symmetry. So we can focus on, say, one valley, valley K. And basically, the BM model is effectively a 4x4 matrix, right? There are these 2x2 blocks, and each block represents a layer. So for example, the top left block, I wish my laser worked. The top left block basically indicates the physics within layer 1. So this is the intralayer physics in layer 1, while the bottom right block is the intralayer physics in layer 2. On the other hand, the off-diagonal blocks indicate the physics of hopping between the layers. And each block itself has a sublattice structure given by sigma. So the diagonal blocks are super simple, right? This is intralayer physics. It's just going to be the Dirac points, right? So we have basically VFK dot sigma, except we have to account for the shift of the Dirac points. But yeah, basically that's it. Obviously, because it's intralayer physics, it's going to preserve the momentum. right? So therefore, it's a delta function in K and K prime. Now, the interlayer pieces are a bit more interesting. So, for example, I have this interlayer tunneling matrix T, and this tells me something about the tunneling of electrons between layer 2 and layer 1. Now, you can actually derive this tunneling matrix in just a few lines. I'll spare you the gory details, but let me say a few properties about this tunneling matrix, right? So clearly, the moiré pattern is fundamentally an interlayer phenomenon, right? So clearly, this tunneling matrix should be sensitive to the interlayer physics, right? To this moiré pattern. So basically, this shouldn't conserve momentum. And indeed, it basically breaks momentum conservation up to a moiré reciprocal as vector Bm. So basically, K and K prime can differ by some moiré reciprocal as vector. Good. Of course, this matrix also has some sublattice structure to it. Now, I've just sort of schematically indicated it with this doodle. But let's try and understand what this structure is, right? So if we were to focus on an AA region, you would naively say that, oh, I guess the diagonal entries should be larger than the off-diagonal entries, because in an AA region, you have literally atoms on atoms, right? So the A's and the A's should be closer, the B's and the B's should be closer. But there's also other regions where, you have AB and BA stacking, where you have the opposite, where the A's are closer to the B's. So if you were to average over the entire moiré unit cell, you would expect that these entries should actually be around the same magnitude, right? And indeed, if you do the analysis carefully, you actually find that these entries are the same magnitude. So let's see how this actually pans out. So you can actually implement this model on your laptop in just a few minutes, and you can generate the resulting moiré band structure, which is shown here. So as advertised, right, so this is a band structure in the moiré-Brouillon zone, and as advertised, you find these sort of nice flat bands. And the bandwidth is really small, right, just a few MeV. And again, there's 8 narrow bands if you account for spin and valley as well. But something funny happens at the edges of these bands, right? You see that at the band edges, right, around nukes to -4 and nukes to 4, there's either a non-existent or a super small gap to the remote bands. And the thing is that this is not that consistent with experiments, right? Because here's a transport experiment. This is a conductance as a function of density, right? And at nukes to -4 and +4, experiments consistently see a very clear non-interacting band gap, a moiré band gap, right? And this is true even at high temperatures where these correlated insulators disappear, and for angles slightly away from the magic angle where the bandwidth isn't flat enough to get correlated physics. So clearly, there's some discrepancy here, and we need to figure out a way to open up a clear moiré band gap. And it turns out that the culprit is indeed our assumption of a rigidly twisted bilayer, right? And in fact, the system does relax quite substantially, and we can actually understand why the system would relax, right? So let's, again, look at the local stackings of the twisted bilayer, and let's focus on like the high symmetry ones, so AA, AB, and BA. And let's ask which of these stackings locally have the least stacking energy. And it turns out that Bernal stacking, or AB and BA, is actually energetically preferred, right? So if you went into the wild and you found like an untwisted bilayer, it would actually be Bernal stacked, right? And it's quite intuitive to understand, because if you think about AA stacking, you literally have like hexagon on hexagon, so you got these PZ orbitals mashing into each other. But for AB stacking, some of these guys can like slot into the honeycombs of the other. And so basically Bernal is preferred. And so the system, to minimize the stacking energy, would want to try and maximize the area over which it's locally AB and BA stacked. And for small twist angles, this effect is actually really significant, right? So this is a schematic for a small twist angle system, and you literally have AB and BA domains, which is separated by soliton domain walls, and at the corners you have these really tiny AA stacking regions. Now, it's not so severe for the magic angle of 1 degree, but it's still quite significant. And furthermore, you find that at the AA regions, the equilibrium interlayer distance is actually larger, and so the system actually corrugates out of plane as well. So basically, we see that the system actually relaxes quite a lot. So how do we incorporate this newfound information into our model? Well, one way is to simply just modify this tunneling matrix, right? So basically, now that we know that AB and BA are the dominant stackings, right, we would guess that the diagonal pieces of the tunneling matrix is actually suppressed, right? Because actually for most of the system, it's Bernal stacking, so A is close to D and vice versa. So we can incorporate this with this sort of parameter kappa, which is less than 1. We call this the chiral ratio, and this will suppress for us the intra-sublattice hoppings. And if you follow through with the numerics, you find that for a reasonable kappa of like 0.8, the band structure looks like this. So happily, we still get flat bands, right? But now we develop a healthier remote band gap to the remote bands. Now, you can wonder what happens if we take this to the extreme, right? What happens when you set kappa to 0? And in this so-called chiral limit, another Amber Alert, in this chiral limit, basically what happens is that the Hamiltonian is now anticommutes with sigma z, and quite remarkably, at the magic angle, you find that the bands become exactly flat throughout the entire Baron zone. And of course, we have to remember that in this limit, we actually have many bands, and these bands are actually churn bands. So this sort of situation should remind you of one of the great settings, the classical settings for strongly correlated topological physics, which is a Landau level, right? Of course, now it's a bit strange because we have a multi-component Landau level, and we seem to have different Landau levels with different churn numbers or different magnetic fields. But we would expect still a lot of the similar physics, like quantum Hall ferromagnetism. And this perspective, starting from this limit, is known, this perspective in trying to understand the correlated physics from this limit is known as the strong coupling framework. Of course, an important question is, whether the intuition and the lessons we learned from this limit hold in the limit of realistic kappa, like 0.8. Let me also mention that there's another complementary viewpoint, which works better for large chiral ratios, called the topological heavy fermion framework, which is more recent and has been gaining traction lately. Okay, so I think we're finally ready to write down the full Hamiltonian, right? So we're going to take our single particle model, which we'll take as the continuum model, and let's add Coulomb interactions in the sort of usual density-density form. So B of Q here is the Coulomb potential, and let's also remember that we have at least a latent topology in the system, and we can also, let me emphasize, we can also tune the density, right? So unlike 3D crystalline systems, because this is a 2D system, we can surround it with gates, and by tuning the gate density, by tuning the gate voltages, we can actually dope the system. And in fact, you can actually dope right into the remote bands as well. So with all these things, it seems like we have all the perfect ingredients to realize, strongly interacting topological physics, right? And all there is to do, well, I guess it's still an interacting model, but in principle, all there is to do is to attack it with your favorite analytical or numerical technique, right? Like the ones we've heard about earlier in these talks of, quantum Monte Carlo, DMFT, Hartree-Fock, et cetera, et cetera. But life isn't always so simple, right? So I have this question mark in the title. So it turns out that defining the right model can often be quite subtle for these materials. And even if this is the right model, we have to remember that we're doping through entire bands worth of electrons, right? And we have strong interactions, right? So, even the notion of a flat band is a little bit sort of subtle, right? Because, so here, for example, I've just shown some Hartree-Fock band structures, including the Hartree-Fock self-energy. And you can see that for TBG in particular, as you dope through different filling factors, the bands can warp and deform quite significantly. So the notion of a flat band is also a little bit subtle. But anyway, I think enough theory for now. Let me now take a brief interlude to talk about the experiments. But before that, any questions so far on the theory? Yes? So that is one way to correct for it, but I will show you later some ideas. Actually, more external factors. I'll tell you about it later. Yeah. Okay, any other questions? Good. So yeah, so this is at the heart, a experimentally driven field, right? And it's truly remarkable, the rate at which experimentalists have been able to fabricate and improve on the devices and to find new discoveries, right? And it's usually a field where theorists are playing catch up. So I think it's only right that I sort of showcase some of the early landmark experiments in this field, and hopefully this will help you to firm up some of the ideas I presented on the previous slides. So, the field really started in 2018 with this twin pair of experiments by the Pablo Herrera group at MIT, right? These are primarily transport experiments. And so in this top panel, I'm just showing you the conductance as a function of the filling factor, right? So again, in these systems, you're able to tune the density in situ, right? And on top of the band insulator, right, at plus or minus 4, you also see a semi-metal at nukes of 0. And this sort of makes sense, right? We're not H-bin aligned, so we have C2, and hence we have Dirac points of neutrality. But the strange thing is that they observe these sort of insulating behaviors at nukes of plus or minus 2. And this is a bit strange because given the spin and valley degeneracy, we'd expect that we wouldn't expect an insulator at this filling. So clearly this is a correlation-driven insulator. And if you were to zoom into the fillings around minus 2, you would see that there are these superconducting domes that flank the insulator. And the TC can be up to a Kelvin, which doesn't seem very large, but you have to remember that the Fermi temperature is quite small because the Brouillon zone is really small. So this is actually a relatively high TC superconductor. And this really attracted a lot of attention, especially because of the resemblance to the high TC Coop rates in these phase diagrams. As I alluded to earlier, later experiments also saw signatures of time versus symmetry breaking and topological transport, right? So in David Goldhaber-Gordon's group, they measured the anomalous Hall effect as well as hysteresis at nukes to 3. And later on, Andrea Young actually measured the quantized anomalous Hall effect at the same filling. And this particular sample by Dima Efetov was quite interesting because, if you look at this bottom plot, there seems to be a lot going on. And basically what we learned from this sample is that, in principle, there could be many correlated insulators at pretty much almost all fillings with many different superconducting domes. So basically anywhere along the density axis between minus 4 and 4, you could basically find correlated behavior. But this is also an early indication that different samples seem to be doing different things.
Excuse me, what does CS mean?
Oh, correlated state. Yeah. You mean this thing?
Yes.
Yeah, I think it just refers to like an insulating sort of feature, a peak. Yeah. So the Landau fans were a nice way, was nice evidence for symmetry breaking, right? So this is basically magnetic transport. This is magnetic field versus density, and the slopes of these lines can reveal information about. These are basically Haas oscillations, right? And the slopes of these lines can tell you information about the Fermi surface degeneracies in your material. And given the spin and valley degeneracies, we expect these to be a multiple of 4, right? And indeed, that's what you see at neutrality. But especially if you get to like 2 and nukes to 3, right, you seem to get these resets. And these lines have a different slope where the Fermi surface degeneracy drops, right? So this is evidence of some sort of flavor symmetry breaking. And a complementary viewpoint is given by the so-called cascade or reset phenomena, where if you look at some quantity like the electron compressibility or the tunneling conductance in STM, you find that there are some features that seem to modulate periodically with the filling factor, in particular every time the filling factor increases by 1. So something seems to be happening at every integer filling, which is sort of suggestive, at least at low temperatures, again, of some sort of symmetry breaking. And even if you don't find Chern insulators at low magnetic field, at 0 magnetic fields, for many samples, if you just apply a small magnetic field, and this is still quite far from 1 flux quantum, you find the presence of many a zoo of different Chern insulators, right? And you can extract the Chern number from the Strata formula, and these Chern numbers are largely, but not always, consistent with what we expect theoretically. So, of course, I'm barely scratching the surface, right? In the past 5 or 6 years, there's been at least 100, maybe even 200 experimental papers just on TPG alone, right? So there are many other topics I haven't managed to discuss. I've only briefly mentioned superconductivity, but there's also been evidence of potential pneumatic behavior as well as unconventional nodal behavior. I've mentioned Chern insulators, but as I'm sure Yongwon will mention tomorrow, there's also been evidence for fractional internal insulators. There's also been, for example, linear and T resistivity. And of course, there's been many different probes that have been used on these materials, right? So transport, that's the obvious one, but other things like ARPAs, optics, a bunch of different things have been done on this material. But one common thread seems to be that there is a substantial variation between different samples, right? So basically, no two devices are exactly the same, right? So in this table by Alan McDonald, basically what he's done is he's asked a simple question, like the most basic correlated question he asks, right? At which fillings do you find a correlated insulator or a metal or a semiconductor in these different samples, right? And what we see is that, okay, it's a bit of a messy plot, but basically, it seems all over the place, even if you account for the different twist angles, right? And this has been well known for a long time. And on this slide, I try to list some different factors or some different parameters that can help to maybe explain why all these samples are giving different results, right? So obviously, there are some things that are easy to control, right? These are things that can be tuned in situ. So an obvious one is the filling factor. You just change the gate voltage, you dope your system. Experimenters can change the temperature at which you do experiments. They can also apply fields, right? So you can apply a magnetic field, or you can apply a displacement field, even in some cases apply pressure. But then here, there's some other things I've listed that are, that the experimenters have some influence over, but it's not always so easy to characterize or control precisely. So, twist angle is an important one because I already mentioned that there's the notion of a magic angle, but it can be quite difficult to target a very specific twist angle. And during the fabrication process, this angle can sometimes change over time. Strain is another one, right? So usually we don't want strain in devices, but often it's an inevitable outcome of our fabrication. There's also the effect of the precise device geometry, right? So usually what happens is that these TBG devices are encapsulated with HBN dielectrics and then covered with metal gates, right? But the precise geometry, like the spacing of the HBN and the distance to the gates, can affect how the interactions are screened in these devices. And finally, I've mentioned HBN before, right? And I've just used it as a way to break C2, but HBN itself will form a moiré pattern of graphene, right? Because there's a lattice mismatch between HBN and graphene. So, theoretically, it's quite complicated exactly how we model the interaction with HBN. And then finally, on this sort of set here, there are some other, theoretical unknowns or things that are even harder to control or measure, right? So given how complicated a moiré unit cell is, right, are we really confident that we captured all details of the model correctly, right? There's also, the emergence of many new types of moiré phonons, right? How do they couple to the physics, right? And finally, there's this sort of rather nefarious type of disorder, which is unique to these moiré systems, which is a notion of twist angle disorder, right? So, even with relaxation, I've always sort of assumed a globally constant twist angle, but these are, micron-sized samples, and this twist angle can vary over the whole sample, right? And theoretically, we don't really know much about how to deal with this, but experimentally, we know that it is there, right? So, for example, in this paper by Eli Zeldov's group, what they've done is by measuring the lambda levels, they're able to basically map the local twist angle in these devices. And you can see that the variation can be several tenths of a degree, right? And this is quite expensive because the magic angle range is also several tenths of a degree. And furthermore, the twist angle, it's not some like random Gaussian disorder, right? It's often very correlated, right? You find these mesas, right? And there are very sharp steps in between different regions, right? So all of these factors can come into play. To briefly illustrate how important these factors can be, let me just focus on one particular variable, which is strain, right? And I've picked this one because I've also been involved in the theory of this some while back. So let's go back to our putative Hamiltonian, right? It's an unstrained model. I haven't added strain to it. And let's say you were to solve it with your favorite numerical tool. Well, what you'd find invariably is that at any integer filling, you'd find that you obtain a gapped correlated insulator, right? And this is consistent through many different numerical techniques. which sounds good, right? Because we know that TBG experimentally has correlated insulators, so it's great that numerically you find that to be true. However, one issue is that experimentally, these particular fillings, which is neutrality and nukes to 1, by and large, are not insulating, right? You either find a semi-metal or a metal, but these are often the fillings where actually the numerics find the most robust insulators. So there is some tension here. Yes?
Yeah, possibly related to you once asked the question about the correlated insulators. So this really the modify because you do the hard work.
Yeah, so I think in the very early days it was sort of labeled as MOT-like, but I think it's more complicated than that. And we can discuss about the true nature of that later. Yeah. But yeah, but actually it turns out that in this sort of unstrained model, Hartree-Fock actually does really well compared to other highly correlated techniques. So in this limit, at least, it's actually sort of quite determinant-like. Okay, so yeah, this is tension here, and I mentioned strain. So one factor that's been known to plague TBG devices for some time is strain. So how do we know this? Well, you can literally see the strain in STM, right? So if you image the moiré lattice, which is shown here, you can see that maybe from this side, you can see that the lattice vectors are slightly strained or sheared, right? And what people find is that the strain is pretty much ubiquitous across pretty much all devices, right? And what you can do is you can ask what happens to your single particle model when you add strain. And if you put like your reasonable value of strain into your single particle model, you find that your resulting bands actually get a lot more dispersive, right? And so you're left wondering, maybe in the strain model, are we really in the limit of super strong interactions? Maybe you're in this more intermediate coupling regime, right? And you may ask yourself, do you still get correlated insulators, right? For now, I'm still focused on that limit. You can actually include the other bands. They do end up quantitatively affecting the physics a little bit, but I'd say that the quantitative phase diagram is relatively unchanged. Of course, it does depend roughly on what your chiral ratio is. If your chiral ratio is very large, then the band gap is really small, and you really have to worry about the remote bands. So this is something that I addressed a few years ago. And so this is a Hartree-Fock phase diagram. Let me not get into the details. I don't think I have time. But the main message is that we found this new sort of order, which we call the incommensurate Kekule spiral, or IKS. You can ask me later what all these words mean. But basically, we found that for a small amount of strain, this new order seems to dominate the phase diagram. And importantly, at nukes to 1 and nukes to 0, we found that the system became gapless, which is nice, right? But crucially, at nukes to 2 and nukes to 3, this state remained gapped, right? Because it would be a shame if all of the gapped insulators disappeared. So at least within Hartree-Fock, it seemed like this is a step towards bridging the gap with experiments. And there's also been some DMRG studies, which also recreates some aspects of this phase diagram. And more recently, there's been this tour de force STM experiment last year, which basically measures, by using high resolution STM, they can actually measure the microscopic sort of order parameter in TBG. And what they saw was that in typical strained TBG devices, they seem to have found order that's consistent with this incommensurate Kekule spiral, whereas in rare ultra-low strain samples, they find a different state, whose identity is still under debate, but it's probably not this state. So I think this is a valuable lesson in carefully thinking about the effects of all these other factors in understanding the correlated phases of these complicated materials. And a lot of these factors, to various degrees, also affect other moiré or super moiré systems. Great. So talking about other systems, I think that brings me to the end of my first part, which was focused on TBG. So any questions at this point? Yes?
Yes, so the superconductivity you mentioned on the unique node, do you have the pairing symmetry way?
So experimentally, yeah, there's no experiment so far that have determined that pairing symmetry. I think theoretically, it's still at the stage where I think people have proposed all sorts of things. So I think we're still not yet, as a community, we're still quite far from converging on a pairing symmetry or let alone mechanism. So we're not there yet. Yeah. Okay, good. So in the remaining time that I have left, let's say just 5 to 10 minutes, let me sort of say a bit about things beyond TBG, right? So obviously, TBG started this whole field, and to this day, there's still a lot of active research, both experimentally and theoretically. But one reason that this field of moiré has continued to prosper is that there's been a lot of interesting and new results on systems that go beyond twisted bilayer graphene. So here I've sort of collected a very biased and partial list of platforms that are not TBG, right? So obviously you can consider variations of graphene, right? So usually this means just putting more layers, right? But there's many different ways of aligning the layers, right? For example, imagine that all your layers are twisted, right? Maybe in an alternating way, right? Or you consider, for example, n plus n twisted graphene, where you have like an m layer untwisted stack and an n layer untwisted stack, and you have one single twist, right? And you can also take your graphene system and you can sort of couple it with a different material like HBN or a transition metal like chalcopyrite. Talking about other materials, you can also consider completely different material platforms, right? So you can consider TMDs, right? And so first of all, you can consider heterobilayers versus homobilayers, right? So for heterobilayers, because you're considering two different materials, then the lattice mismatch automatically gives you a moiré without twisting, right? But you can also consider homobilayers where you just twist it in the usual way. And of course, you also have different types of TMDs, right? So most TMDs are hexagonal, but you also have rectangular TMDs like tungsten titelluride. These are still like regular electronic systems, right? You can also twist other things like magnets, like chromium triiodide, and you can even twist things like cuprates as well. So let me just say a few things about some of these guys, right? So I think the simplest extension is just to consider twisted trilayer graphene, like 3 layers of graphene, right? So now we have 3 layers, 1, 2, and 3. And now we realize that we have 2 twist angles which is independently tuned, right? Theta 1, 2, and theta 2, 3. So suddenly our world seems a lot more complicated. But let's just think about some simple cases, right? So probably the simplest case is if you consider what we call twisted symmetric trilayer graphene, which is where theta 1, 2 is the opposite of theta 2, 3. So basically you take one layer, you twist the second layer, and then you untwist the third layer. So actually layers 1 and 3 are aligned. And what you realize is that you can sort of play the same game as we did for TBG. And if you just draw the Brouillon zones of the 3 layers, you realize that because layers 1 and 3 are aligned, you basically get the same moiré Brouillon zone. So you still get a single moiré pattern, right? And what's more, you can go through the same analysis and look at the band structure. So you can write down a similar Christian to McDonald model. Now it's a 3x3 block of 2x2 matrices because you have 3 layers, right? But you can actually decompose it into the mirror sectors. And what you actually find is that this Hamiltonian decomposes into a renormalized version of TBG and a single graphene Dirac cone, right? So here I've just lifted a band structure from some paper, and you can see that, here you seem to see the familiar twisted bilayer graphene band structure, but then you also see this very dispersive Dirac cone, which is coming from this, which is, I believe, the mirror odd sector. And so basically, it seems like twisted trilayer graphene, on some level, has quite a lot of resemblance to twisted bilayer graphene. And actually, you can do this same construction for 3 layers, 4 layers, as many layers as you like, right? And indeed, you can find this similar sort of decomposition. Yes? That's right. That's right. That's expected to be quite weak. Yeah. And of course, also let me mention that the daggers on the teeth, that's just coming from considering the relative twist angles for any 2 layers. Good. So as evidence for the similarities of these different materials, right? So here is an experiment showing, I guess, the resistivity as a function of temperature for 2 layer, 3 layer, 4 layer, and 5 layer alternating twist angle graphene, right? They all superconduct, right? But there's also some differences. So for example, you can see that the top is trilayer, the bottom is pentalayer, right? You can see that for pentalayer, for example, the density range over which you find superconductivity is really huge, right? It goes from 2 to 5, right? And so it seems actually that superconductivity is more robust for trilayers and quadrilayers compared to the bilayer. Let me also point out that, actually, recently they've also found the same incremental calculus spiral order for trilayers as well. So there does seem to be quite a lot of parallels with the bilayer. Okay, so that was a system which was very similar to bilayer graphene. Let's consider a different limit. So this is what I call helical trilayer graphene, where this time the two pairs of twist angles are the same, right? So we basically sequentially rotate the 3 layers of graphene. Now, you can again try and play the same game to figure out the periodicity of the system. And what you realize is that, okay, between layers 1 and 2, I have a B moiré, 1, 2. But then if you consider layers 2 and 3, you get a different vector, B moiré 2, 3. And these 2 moiré vectors are themselves slightly misaligned, right? So basically what you realize is that you get a moiré of moiré pattern or super moiré pattern, right? Which is set by the distance between these 2 moiré vectors. So starting from a microscopic lattice scale of a few angstroms, you realize a moiré scale of 10 nanometers as before, but really the true periodicity is on the super moiré scale, which is now hundreds of nanometers. So we get a strange separation of scales between the graphene, the moiré, and the super moiré. And you can imagine that because these scales are so big, that relaxation is now super important, right? And indeed, that's what people find. So this is a sort of a numerical simulation at the super moiré scale. So this is a super moiré length. But what you find is that if you do all the lattice relaxation, you find that the system relaxes into super domains, right? Just as we saw on the moiré scale, now just happening on the super moiré scale. And within each super moiré domain, the system locally looks moiré periodic, right? And so we get this strange thing where we can sort of think about the physics at the moiré scale, but now we just have to stitch them together with these super moiré domains. And we can do similar games with the BM model. I won't go into details here, but again, experiments. So this is a collaboration with Pablo Arroyo at MIT. Again, we can find slightly complementary physics, but still, the same sort of pattern, strongly correlated physics, and anomalous Hall behavior. Finally, I think for the last example, let me just quickly discuss the case of TMDs, because this is a completely different material platform. So what is a TMD? It's this sort of compound where M is a transition metal, usually molybdenum or tungsten, and X is a chalcogen, sulfur, selenium, or tellurium. And it realizes at the monolayer level also a honeycomb, except now that you have different atoms on the 2 sublattices, and also it has a 3D structure to it, right? And the key point is that the monolayer band structure is different from graphene, right? So basically, on some level, TMD is like a gapped version of graphene with strong spin-over coupling, right? So first of all, you notice that there's a huge gap in neutrality, right? Now, the electron side is, the spin-over coupling is quite weak, so let's ignore that. But on the hole side, you find that the spin-over coupling is really strong, right? So this spin-over gap is around a few hundred MeV, and basically you find that the band closest to neutrality is spin valley locked, right? So in valley K, you find a spin-up band, and in valley K prime, you find a spin-down band like this, right? And you can sort of play similar games with the moiré pattern. So again, let's twist 2 TMDs together. And what you tend to find is, again, flat bands. In this case, now it's the top valence band is a flat band. Usually people find that it's a valley turn band. And this time there's some differences. So first of all, it's spin valley locked. So we've lost one flavor of degree of freedom. And furthermore, there's no longer a stringent magic angle requirement, right? In these models, people find that whether you're at 1 degree or 5 degree, these bands are relatively flat. And another nice property of these TMDs, even though transport is a bit more difficult because contacts are hard to make, but these materials have a very strong optical coupling, which is also valley resolved. So by shining circularly polarized light, you can selectively couple to different values. And one reason that these materials have been super hot is the emergence of, within the past year, of several reports of fractional turn insulators in these devices, which again, I'm sure Young will address tomorrow. So I think I'm out of time, so let me return back to my outline slide. So I've mostly told you today about twisted binary graphene, right? I hope I've sort of outlined some basic arguments about how to understand these materials. And I've also shown you a bit about experiments and some of the complications that can occur. I've also said a few words about other systems. And yeah, I hope that was useful, and I'm happy to take any questions.
Suppose you have a sort of flat band. Why is that TMD? Never anybody see superconductivity and things like that.
That's a good question. So actually, within the graphene systems, one potential clue is C2 symmetry, right? So it turns out that within all the at least almost all the superconducting candidates, right, like TBG or twisted trilateral graphene, all of them have C2 symmetry, and all the ones that don't have C2 symmetry don't have superconductors, and all these TMDs also lack inversion. So I don't know whether there's any strong theoretical reason, but at least phenomenologically, that's a common pattern.
I thought, in graphene, the graphene is unconventional, right? Not BCS, right? Why symmetry?
You mean a twisted bilateral graphene?
Yeah.
It's not clear. I mean, it's nodal.
It could be BCS.
I don't want to say it on recorded. But I think similar needs to be qualified. It probably isn't fully BCS. I agree, but I think there's still a lot of leeway into is it phonon assisted Coulomb, or is it really fully fluctuation mediated? And that's still unclear. But I think one thing I'll say is that the fact that so many different graphene materials, even though the band structures, I show you that the trilayers have, on some level TBG hidden within it, but we talk about 5 layers versus 2 layers, so there seems to be a lot of variation. And also talked about strain as being one big change, and somehow all these devices still superconduct, so whatever mechanism there is, it has to be robust enough to survive all these different changes. So
if you compare difference of the number of layers in the superconducting phase diagram, can people actually make the plot, compare with the doping, function of doping, and compare with the cuprate and the typical?
So for example, let me first address, even within one set of layers, like say 2 layers, right? You can try to make the plot, it's all over the place, right? And I think it's quite difficult to control, yeah, because it's all these other factors. I don't know which factors are the most relevant, but these other factors really do affect, even within one material class. Yeah.
Okay, we still have some time for the questions. Okay, please.
Quite a bit of phenomenology which looks similar to the correlateral materials.
Right.
So I was wondering, theoretically, if you start from this chiral limit, is there some pathway that one could get to access this kind of correlation aspect of physics?
So I think if you start from this chiral limit or this sort of strong coupling framework, right? So one route to understanding is that actually in this chiral flat limit, okay, it's probably too far early in the slides, but you can actually show some exact results at integer fillings at least, and you can use that as a springboard to do some perturbative analysis, right? About what precisely are the correlated insulators, right? And in fact, the results that you do get are consistent with just working in the realistic limit and doing like a Hartree-Fock or an ED calculation. Right, but this is still assuming the absence of these other effects like strain and stuff like that. You can get a lot of mileage theoretically from working in certain limits, right? Now let me just caution that I hesitate to say strongly correlated because even in the strong coupling limit, it's still actually the exact state that you get is still a Slater determinant, right? It's just a particular choice of flavor ordering you pick out, right? Obviously, as you move away from the chiral limit, it starts to develop fluctuations, but it's a sort of strange limit. Yeah.
Maybe I can narrow down the question. So I was more thinking about norms of superconductivity.
Oh, right.
And then strange metallicity.
Right.
And this sort of aspects. It's just wondering whether the chiral limit could be a starting point for access.
I'm not sure whether the chiral limit is I think actually the heavy fermion framework might be a more useful limit because
that's a more direct.
That's right, yeah, because you really have a notion of having a possibility of local movements, ordering or not ordering or fluctuating. So I think for those sorts of questions, especially for things like If you want to ask, for example, find temperature and strange phenomena there, like I guess either linear T or the Pomerantz effect, right? I think that other framework might be better to understand these things. Yeah. At least for me, I don't know how to understand it from the chiral limits. Yeah.
Okay, thanks. We still have time for one or two more questions. Okay, please.
I think it's not completely known. I mean, I've seen some papers. There is one paper that argued that as you increase the number of, so I've been showing mostly non-interacting band structures, right? And the question is, what happens as you dope these band structures, right? Because really, it's the doped band structure that tells you whether you have whatever you want to see, right? And I've seen arguments that, for example, if you have more numbers of layers, right, basically, so there's two effects, right? First of all, you have these other bands that you can fill, right? So, if you change your doping from 2 to 3, right, for bilayer, you really change your doping from 2 to 3, but in these other layers, you have these other spectator bands that you also dope as well, so you have a larger cushion. And I've also seen arguments about how the Hartree electrostatic effects can mean that the bands remain flatter for longer amounts of doping. But that's the theory that I know of at the moment. Yeah.
Okay, because we are out of time, so let's thank the speaker again.